Section 7.4 here, we're going to get into chemical reaction equations. And as we've mentioned already, there are certain things that are evidence that a chemical reaction has taken place. Change in color, sometimes change in state of matter, change in appearance, usually except for changes in state of matter. And so then we can write a chemical reaction equation to show that. When we do that, you have a arrow, and that will separate your reactant side, the chemicals that you're starting with, from the products. Reactants are written over here on the left-hand side. Products are written here over on the right-hand side. And I should say for all of these, it's reactant or reactants, product or products, because there are some reactions that just start with one chemical that breaks down. There's other reactants that involve chemicals combining to form just one thing, and so those can be singular or plural there. And then the delta sign here is sometimes used for heat. Sometimes heat is put into the reaction equation itself. I'll also say that other special conditions are recorded there. And so that can be something like the addition of a catalyst, or you need a acid or base to get it going, or a classic example is photosynthesis, the process that goes on inside plants where they turn the carbon dioxide that they take in and the water that they pull up from the roots, and they react them to make sugars. And in that process, you need light to get that reaction going. Well, that's a special condition that is necessary. And then in addition to that, we will denote states of matter, and they are usually denoted in parentheses. They're usually touching the chemical symbol. And so, for example, water, as you know, is a liquid. And so we'll have it touching the symbol. As a side note, I tend to do cursive to show the italicized, especially with L, because it looks like a 1 and an I without the serifs. And so I just prefer to go cursive on my lowercase l's. But G for gas, the one that is probably unfamiliar to you, AQ for aqueous, which means that it's dissolved in water. So it will behave like a liquid even though it's not a liquid. And so over here is a table that lists all of those things. And to be honest, I think that's better, even though we just went through the prior slide. And so here we go. In addition to that, a reaction equation has to be balanced. That is, the number of atoms that we have on one side has to equal the number of atoms that we have on the other side. So you'll notice we start here with an O2 molecule. The oxygen in the air is O2. It's what you and I breathe in. And that O2 can react with hydrogen gas to form water. Well, there's two O's. They're going to end up splitting, and so you end up with an O here and an O here. Well, it's not enough to have one hydrogen molecule for that to happen. They'll split, and you end up with an H and an H attached to this one, but that's not enough. And so it actually turns out that it takes two hydrogen molecules here, and so we have to have that. Now, what that means is that we're obeying something called the law of conservation of mass and matter. And I should say, usually it's mass or matter. You'll hear it both ways, usually not mass and. And so we have to have the number of chemicals equal on both sides. We can't create atoms or destroy atoms as Dalton's law tells us. And so because of that, we have to start with a certain number of pieces and end up with those same number of pieces. And so what happens in a chemical reaction is the bonds that exist are rearranged and we end up with new substances, but it's new substances made up of the same pieces. Now, something that they don't actually show here is how you go about balancing. Because if you know that hydrogen gas is reacting with oxygen gas, and you'd be told that they're both H2 and O2. I think we maybe even mentioned that previously, that they are diatomics. And you know, of course, that water is H2O, but you'd be told hydrogen and oxygen react to form water. Well, you know those are your initial chemicals. Well, what we can do then is we can count how many are on each side. And so over here, I have two hydrogens, and I have two hydrogens here, so my hydrogens are equal. And you may be saying to yourself, wait a second, there's a 2 down here, and I know I needed 2 of them. That's okay. What happens is as we do this, there's a lot of guess and check, and sometimes you'll have something that's balanced, but to get something else to balance, like the oxygens here, we're going to have to change the number of oxygens. And so then to do that, it ends up affecting our hydrogens, and we have to change our hydrogens as well. So anyway, our hydrogens are balanced right now. Then we have our oxygens here, and there's 2 oxygens, but over here there's only 1. Well, I can't change the formula here. There's this old lame joke, and I apologize if I mentioned it before, but 2 men walk into a bar, and one says, I'll have some H2O, and the other one says, I'll have some H2O too, and he dies. Well, H2O2 is hydrogen peroxide. Of course, he meant 2TOO also, but hydrogen peroxide. If you change the subscript on this, you no longer have water. And we said that these two react to form water, not these two react to form hydrogen peroxide. So we can't change a chemical formula. Because we can't change a chemical formula, then what we do is we insert coefficients into the equation. And so coefficients are multiplicative. They're not additive because there's an invisible one here. We're not adding 2 to 1. It is a multiply, and it is distributive, which means it applies to each of the chemicals in the formula, each of the atoms there. And so now we have 2 times 2, or 4 H's. And here we have 2 times 1, or 2 oxygens. Well, over here we still have 2 oxygens, so my oxygens are still balanced. I suppose a comma there maybe to emphasize that that's not a number. But my hydrogens are now screwed up. I've got 2 times 2, 4 hydrogens, and so I need 4 hydrogens over here. So the way I fix that is by putting a 2 coefficient here. I always recommend at that point that you go back and double check and make sure that everything is balanced, because frequently when you're changing one, it will screw up another, and there you have it. I'm also going to show here on the next example a table that a lot of students will make up, and it works great. If it helps you, go for it. If it doesn't help you, or if you can do it without the table, that's fine as well. So that table will look something like this. You have your chemical, and you'll have your reactant side, and you'll have your product side. And so on my reaction here, I have the aluminum and the sulfur. And to start out with, I have 1 aluminum and 1 sulfur on this side. And on this side, I have 2 aluminums and I have 3 sulfurs. So I need to make those equal. So what do? Well, I can only do coefficients, and they are multiplicative. And so I'm going to do a coefficient here, and I need to multiply it by a 2 to get those 2 to be equal. So that means a 2 coefficient there. And then sulfur, I need to multiply it by a 3 to make them be equal, and so that's a 3 coefficient here. Now, if we had done that on our prior one, then we have a table that looks like this. We had hydrogen, we have oxygen. Over here we have the same 2, and we start out with 2 and 2 on the reactant side, 2 and 1 on the product side. Well, right now those 2 are equal, but then my oxygens aren't equal, and it looks like I'm going to have to put a coefficient on the product side here because currently this one is smaller, so I multiply that by 2, and now those 2 are equal. But that also means I have to multiply this one by 2 because, again, it's here and it's distributive. It applies to both. So now I have 4. Those 2 are no longer equal, so I need to make them equal. So that's going to require a 2 here, which means a 2 there. And so now they are equal again. And so if the table helps you, great, go for it. If it doesn't help you, that's okay. Don't worry about it. Or if you're able to do it without the table, again, that's great too. Here, we just want to state how many are on each side to kind of prove that it's balanced. It's already balanced for us, but here we have 4 phosphoruses, and over here we have 4 phosphoruses. We have over here 12 bromines at 6 times 2, and over on this side, we have 4 times 3, which is also 12 bromines. So we know those are equal. Here we have 2 aluminums and 2 aluminums. I would call this 2 times an invisible 1, and this an invisible 1 times 2. Irons, we have 2 and 2, and oxygens, we have 3 and 3. So they are balanced. This one here is a little bit more open-ended, and it involves the other form of rust here. Rust can be the Fe2O3 you saw on the prior slide, or Fe3O4. It also turns out that it can be FeO, and really Fe3O4 is a mixture of the two, but that's okay. And we're asked to balance this one when Fe3O4 reacts with hydrogen gas, well, hydrogen is always H2, to produce iron and water. And since they mentioned it here in the prompt, I'm going to go ahead and include the states of matter. They tell us solid iron oxide. Of course, anything that is ionic is likely to be a solid. H2, you're told it's a gas. You probably know that it's a gas. Hopefully you do. And so that's that one. Iron, any metal, is going to be a solid except for mercury. And it also tells you here. And then water is going to be a liquid. Are they absolutely necessary? No, you'll see plenty of reaction equations where they are not listed out, but it can be helpful for predicting what's going to happen in a reaction. It's certainly helpful for knowing what you're expecting to observe in a chemical reaction, and it's better and more descriptive. And so if you're told it, go ahead and include it. Here we have 3 irons. And over here, we're going to need a 3 coefficient to give us 3 irons. We have 4 oxygens here, so it's going to take a 4 coefficient here to give us 4 oxygens. That gives us 4 times 2 hydrogens, so we have 8 hydrogens on that side. So this one is also going to have to be 4 times 2 to give us 8 hydrogens. And I didn't do the chart this time. And there's plenty of times where, again, you'll balance one, it'll screw up another, and you'll have to fix it, and that's okay. It really is a lot of guess and check. This one here simply mentions that we're going to do an example with balancing with polyatomic ions, but it turns out that this is a type of reaction where we take 2 things that are dissolved. We have something that is dissolved in here to begin with, and we have something that's dissolved in this dropper that's being added in. And when the 2 of these react, this side over here would be our reactants. Some things rearrange and switch places, and then these end up being your products. And one of your products is solid and insoluble, and so we end up getting a solid from 2 aqueous solutions. It turns out that the other piece is aqueous. We'll get into types of reactions soon, and it turns out it's really difficult to have a reaction. It's really rare to have a reaction where you have 2 aqueous substances and both of them turn into solids, what we call precipitates. Anyway, we're going to look at this one on the next slide. So here we go. This is the reaction that we need to balance. And what we can do, it turns out, when we have a polyatomic ion, is if it's the same on both sides, if it doesn't break down, we have the same polyatomic ion here, I don't have to count my individual P's and O's there. So I'm going to show both ways that you can go about balancing this kind of reaction, and both work. One of them is a little bit shorter, but sometimes the shortcut confuses students, and so it's okay if it does. It's not absolutely necessary that you take advantage of the shortcut. So one thing to remember is when we have a polyatomic ion, a subscript here means that we have 2 of the polyatomic ion. And so this 2 is also distributive and applies to both of these. We don't write this out as 2 and 8, but it is really what it means, is that we have 2 of those and 8 of those. So if we just go about balancing this the way that we have the prior ones, I have 3 sodiums here, so I need a 3 coefficient over here to balance out my sodiums. Now I could go back to the PO4, but sometimes when I'm balancing, I like to just bounce back and forth like that. And so here I have 3 sodiums. Well, that gives me 3 chlorines. So I need to have 3 chlorines over here. I have 2. I can't have addition here, and there's no number I can multiply an even number by and get an odd number. So I'm going to have to change that. And so what I'm going to do here is I'm going to go for a 3 there, and when I do that, I have to come back over here, and now I have 3 times 2 on the reactant side, so I'm going to need a 6 here. Well, that then screws up my sodium, so I have to come back here and have 2 times 3 sodiums, giving me 6 sodiums. Then I have 2 phosphoruses because I have a 2 there that applies to each of them. And so that matches as the 2 phosphoruses over here as I wrote it out just a moment ago. I also then have over here 2 times 4, 8 oxygens, as we said a moment ago, and here I have 2 times 4, 8 oxygens. So we're good on the oxygens, and I haven't checked my magnesiums yet, but 3 magnesiums and 3 magnesiums. That was a lot to keep track of. So let's make sure. 6 sodiums on the reactant side, 6 sodiums on the product side. That's good. 2 phosphoruses, 2 phosphoruses. 8 oxygens, 8 oxygens. 3 magnesiums, 3 magnesiums, and 3 times 2, 6 chlorines, and 6 times 1, 6 chlorines. Yes, this one is balanced, and we're done. When we redo this down here, it's going to be the same, but there is a little bit of a trick. You can treat phosphate, the PO4, since it's the same on both sides, as one thing. Like I said, this trick sometimes confuses students, and if you don't get it, you don't get it, and that's fine. Just do it the normal way, like we've been doing up here, and it will work out for you. And for some students, they have no problem handling the trick, but they like to treat this as something else. So if you want to treat PO4 as just say X, and so over here I have an invisible 1 number of X's, and here I have 2 X's, and then just balance them that way, that's fine. I'm going to talk through it like it's the phosphates. So I have 3 sodiums right now, so I'm going to need a 3 coefficient there. You'll notice I end up making the same oversimplification mistake that I make there, but that's okay. Then I have 1 phosphate here, but I have 2 phosphates over here. That 2 means I have 2 of the things inside parentheses over here. I can recognize that that thing would be in parentheses if we had a subscript number out here. But as we mentioned a moment ago, this 2 is distributive to the things inside the parentheses, but I have 2 phosphates. If I have 2 phosphates over there, I need 2 phosphates over here, so that gives me 2 phosphates. I now have 2 times 3 sodiums, so I'm going to have to change this one to 6 sodiums. Then I have 1 magnesium and 3 magnesium, so I'm going to have to put a 3 there. 3 times 1 is the same thing as 1 times 3. Then we have 3 times 2 chlorines, and we have 6 times 1 chlorine, so my chlorines are balanced. It's still a lot, so I'd go back through and double check, but you'll notice it matches what we have above, and we've already double checked what's above, and I've taken long enough on this slide already. So that is how you can balance with polyatomic ions, is just focus on balancing the whole ion rather than the individual phosphoruses and oxygens. Now, it does come out, there's plenty of reactions like the decomposition of calcium carbonate that produces calcium oxide and carbon dioxide. And so you have a polyatomic ion on this side, but you don't have it on this side. And when that happens, you can't use that shortcut. However, I do want to use this reaction to point out something, that here we have 1 calcium and 1 calcium. We have 1 carbon and 1 carbon. We have 3 oxygens, and we have 1 plus 2 oxygens. That's 3 oxygens. This one's balanced already. You don't need any coefficients on this one. It's balanced already, and it's totally okay to have invisible ones all throughout. It's totally okay to have, and we've seen this a couple times already, but I haven't emphasized it, chemicals that don't get a coefficient. It's of course an implied invisible one there, but some chemicals don't need to be multiplied for the 2 sides to be equal. Acid-base reactions are similar. So this one here actually has a polyatomic ion in it, the SO4. And so I can focus on balancing just the SO4s, although it turns out there's 1 of each already. So hopefully we don't need any coefficients. If we do, it'll be the same coefficient on each. However, something special that happens in acid-base reactions is the base always contains OHs. And an acid always contains H's, although that's not super important for the trick I'm going to show here. It turns out you can write water as HOH. It's still H2O. But when you do this, then what you can do is you can balance the H's with the H's, and you can balance the OH's with the OH's instead. It's a little bit weird to think of on the product side there, the H here separate from the H here, so this is where that X trick works, and you could treat this as HX and NaX, and then just balance the H's and the X's if you prefer that. But if you treat water as HOH, it helps save you a little bit of time. And same thing with balancing the polyatomic ions. So I'm just going to do this one through with the shortcut method. If you want to do it the longer way, it's fine. And as always, I encourage you pause this and try it on your own before you watch the solution here. Anyway, I have 2 H's and I have only 1 H over here because again, I'm ignoring the OH. So I'm going to need a 2 coefficient there. That gives me then 2 OHs also, so I'm going to need 2 OHs. That gives me 2 NAs, so I'm going to need 2 NAs. Oh, I've got that already, and I've got 1 sulfate here and 1 sulfate here, so I should be balanced already. Double checking the answer. I've got 2 H's and 2 H's. I have 1 sulfate and 1 sulfate. 2 times 1 sodiums and 1 times 2 sodiums, 2 times 1 OH, and 2 times 1 OH, we are balanced. And that works for absolutely every acid-base reaction. This one here kind of shows you what it would be like if we do this as a multiple choice question where each of these would go with one of the blanks. Personally, when I write a question like this, I would have this answer be 2 blank 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 is how I would show it, and those blanks of course have implied invisible ones there. But really, as a multiple guess, it's just a way to help check your answer because you don't actually know before you start this. So I'm going to need 2 irons there to match the 2 irons over here, 3 oxygens. I can't make those 2 match, so I'm going to have to do a 3 there and a 2 there, which is going to change this one to a 4, and then 3 carbons, 3 carbons. So 2, 3, 4, 3. That is number 2 there. This one here, going to need a 2 there to make my aluminums equal, a 3 here to make my oxygens equal, which means I need a 3 there. So 2, 3, 3, 1. That is this one. And our last one here, this sulfate here jumped out at me, so I'm going to go out of order here. I've got 3 sulfates there. That gives me 3 H2s, so I'm going to need 3 H2s there, and I've got 2 aluminums, and so 2 aluminums. Order doesn't matter, especially because it's a lot of guess and check, but 2, 3, blank 3, 2, 3. They've got it as 1, 1, 3 there, so there you have it. And that finishes section 4.